recording and Freigabe and screen sharing. Okay. Good. So you should be seeing the screen from the virtual machine, and today we'll be doing something very hacky. That is, we will first create just some normal C++ classes, and then we will try to interact with them from C itself without using any compiler support for C++. Create new project. Next, C++ hacking will be the project name. This can go away, this can go away, this can go away, this can go away. So first things first, we might switch this to a C class. So rename to a C file, I mean. So the compiler will compile files differently depending on whether they have a CPP or a C extension. And generally the language is kind of similar, but if you have so C++ code will not compile in a C file, obviously, but C code, if written the right way, will compile in a CPP file. In principle, the only relevant change that you might encounter when just pasting a C file into a CPP file is that if you assign pointers without casting operations, then that will fail, because C itself just checks whether the type is a pointer, but doesn't check to what is it a pointer to. So if it's to a struct, to a int, to a ball, it doesn't care. It just allows you to do that in the most cases. While C++ always checks the types. So if you paste some old C code into a newer C++ file, then this might be one of the changes you will need. That's the most likely change that you might need to do, because in the past people just tried to save time and typing, so they didn't do any casts if the language did not require them. Okay, so we have our C file. Let's include a few things: std.ioh and std.lib. So we can printf stuff, and now let's create a new class, which we will be then interacting with. So we create a class. Let's call it my class. Oops. C my class. So my class without a C, base class, no base class. Okay, so yeah, I don't like the structure, so let's add filters. Let's move the CVP stuff so that it's close together. Oh, that was the wrong file. This one stays here. Okay. So one thing, of course, one might wonder is, so if we have some sort of C++ anything, how can we interact in a, let's say, nice and correct way from C with it, in any way? So first here, of course, we'll make our class to be able to do something. See my actually see my class. Then we want a destructor for it. For now we just leave it as is, and let's just add some simple, maybe a variable int var1 and the function void function1, which we will make print something. I can write it here. Need to add the includes. Printf my class, and let's write it shorter. Func1, my class func1, yeah, \n. Okay, so like that's the bare minimum. Okay, and let's go to our CPP file. So one thing you can do in a C++ file is you can use the extend C statement to say that you want to write something that is mostly just C. And not quite, but mostly. So, and that the thing is that from within such a thing, so here we could have, for example, a function int my C func. Just yeah. Let's print f it something. 1, 2, 3 \n. Or let's just write this. Maybe it's better. Zack. Okay. And now, if we are in a normal C file, we can define a function prototype. We forgot to return a value. That will complain. Oops. Return 0. And now when we run it, it will just call this function. So we can easily make functions which we put somewhere inside a CPP file be callable from a normal C file. Regularly, if we forget this, that should not compile. Yeah, as you see, it says there is an unresolved symbol in my cfunc. The reason is that the way functions are decorated in C++ is different than in C. Decorating functions means the string used as a function name, which is then used in the object files or in the export tables of a DLL, is mangled with some additional characters to make it distinct. Especially, for example, if you would have multiple functions with different arguments. This is something you can do in C++, as you know, which you cannot do in C. So here all the argument types become part of the name so that it is unique, even if technically there would be two functions with the same name. But if we define something as extend C, then it will be treated like just C code, but with the difference that from within this thing we can actually use all the C++ functionality. So for example, we can create a class, then we can call func1 on it, and it will, as you see, also work. So this is somehow like a in between C and C++ worlds. It will usually enforce the more strict casting rules of C++ and so on, but as said, it is easily callable from just C. But of course, this is not quite what we want to do yet. So what we will want to do is really to create a class, interact with a class, and so on completely from C without having any C++ function that would help us in that. So first, let's make our class a bit more complicated. So let's add a second function to it. Func2. Therefore, of course, is func2. And let's make those things more exciting. So let's make it virtual. Func1, this stays as is. The destructor should be also virtual. That's better. We can add some. We can add some non-virtual function. Non-virtual void, just void. Func3, which let's say we'll call a virtual function. Func2. Okay. And maybe let's initialize our variable somehow. So let's say int var var, and here maybe a different argument so that we can always instantiate it even if we don't care to assign something. Okay, and then let's of course also make a derived class just for fun. Since we use virtual functions, I want to have my subclass public my class. Public. Let's be lazy and copy this. My subclass. Let's say we will just pass the thing. That's even easier. But we can add int var2, so that we have a second variable here, var2, and let's say this will be equals something. Doesn't matter really what. And we will copy our two virtual functions. But we will of course change the names here so that we see that which of those we have called. Okay, so far obviously so clear. We haven't done anything particularly hacky just yet. So let's see where we go from here. So we go to C++, and the general idea, as you might remember, is that such classes are in principle very much like a struct, just that it's structured in a particular way. And all the functions, they are just normal functions where the first argument is the implicit argument to the this object, so to the thing. So while it kind of looks very different between C and C++, really what happens under the hood, as you might remember, is quite similar. So thus we should be generally able to replicate it. So let's go here to our C function. This we can leave there, and let's first define two structs which will represent our two classes. So we need something to access. Of course, we could access everything just by offsets, but that would be annoying and it wouldn't be useful. So it would be useful, but it would be just too much work. So let's do it the easy way. Just let's be faster. Struct as my class. So to differentiate it and ensure that we don't use the same name in the project, the classes are called CMyClass, while the structs are SMyClass. So they're just prefixed with a different letter. And as we know, such any class which has virtual functions will have first the pointer to the function table which describe the particular class it is. So void asterisk table. So this is basically a pointer to an array of function pointers. Int var1, the var1 is as it is, and then the next one, the my subclass, will have here just the base class b or base asterisk why is complaining. Okay, we need to do the old star way. Type def struct. C++, just C is a bit annoying in the way that it, even if it's set modern, that it really uses this very old mechanism. So you can define a struct, but if you want to use it as a type, you need to type it explicitly. In C, obviously this is not needed. You just write struct something, and then it's fine. Okay, so we have those two things. The next thing which we will want to do will be probably something that will allow us to access the functions here in this in this virtual table. So we'll create an enum. We don't really need to give it a name. And we have first the destructor, that will be the first function with the index 0, and the rest func1 index will be just incremented one by one from there. So if we would have like a func4 which would be virtual, then it would be like here at the value number 3 and so on and so on. And of course if we would remove the destructor, then we would need to remove it here, because then there is no entry for it. Okay, so we have defined basically what we expect there to be, but we have not yet done much with it. So what we, for example, could now do is to create our own implementation, so that we can basically fully replicate the behavior of our C++ class just in C, and then we can see how we can mix and match those things together. So for example, we can extend our example here to call the function number 3, was it? Which will then call the function number 2, and it will print those things. Actually, we could even make it like this, that we say it should print both things, plus it should print itself once it's done. Okay. Yeah, func3, let's run it. Alright. We should also add for the constructor and destructor and constructor some printfs as well, so that we know that those things also have happened. Tilde. With the subclass, same thing. Maybe I prefer it to be the first, but it doesn't really change anything since we don't print anything else. Right, and then we'll also add a destructor here. And just for completeness, we don't need to specify those things here as virtual. But what we can do, we can add to indicate that it must be overwriting an already existing virtual function. Good. So when you run it will of course now print all the constructors. We only instantiated one of them, so let's try to instantiate the subclass. That will be more interesting. Right, so we have both constructors, then we have the functions where they should be. Then we have the destructors, and we are done. Okay. Okay, so how do we replicate it? Well, first thing, of course, we will need to have the same functions that we already had implemented in the other thing. So void base func1, and it takes as an argument. Did we define this as const or not? We did not. So just void asterisk object. We could also use this capitalized, like this. Like using just this is not recommended because this will conflict with the normal this keyword which exists. So like this, and then we just can, in principle, let's copy the thing here. Zack. But we will call it S. Then we of course do the same thing. Then we of course do the same thing for function 2. Then we do the same things for the derived functions. Sub my subclass as my subclass. And now what we will need are the function tables. So void base v table is equals. Okay, so what are our function? A function of void asterisk function, and we want to assign the value base func1. Then we repeat that with the second one, base func2. And then we do the same thing for the subclass. Okay. Good. So we have this, and then of course calling the functions now would be a bit inconvenient, so we will add wrapper functions that will help us make those things more elegant. So void func1, which takes as my base asterisk object. Did I call it like this? Sorry, as my class subject, and then we need to cast everything. So void asterisk. So void asterisk. Void, oops. Void asterisk. Then the whole thing gets wrapped. So that's a type. Object. A vtable at index. Func1 index. And we pass the object argument to it. And we are missing one bracket, yeah. Okay, then same thing for the function 2. Function 2. Good. Good. So let's test if it does what we expect it to do. So we will create first an instance just of the base class and just make it do something, or we could actually just go for the subclass instantly. That's maybe more interesting. My subclass s is equals this. We don't need malloc size of my subclass. We might have a few too many castings. Maybe not all were needed, but this should be fine. Let's see. This is totally fine, because here it is really just cast as a void pointer without specifying anything. Here we need to cast it to the right type. So this was needed. Then let's continue. So sanity check. If we fail to allocate memory, then return. Actually, let's put this into our own function. Test1. Test1. Okay, and if we allocated it, then we need, of course, now to do what the constructor would have done. So first of all, it assigns vtable1 to our sub vtable. Then the base punct mvar is equals, let's say, 1, and s var1. Actually, we could make like a constructor for that. So do we want to do this as a return value? Yeah, why not? Subclass, and we had like int var as an argument for that thing. So we will. So here it returns null if it failed. If it didn't fail, then it returns var, and the other one was it var1? Oh, I think the other one was called var2. We don't want to have a name conflict. Not var1. Base punct vtable var1. var2 is equals, I think that was var times var, and turn s. Okay. And we can of course also make a destruct, although this one will be kind of boring because it just takes this thing and well, technically it should call the other destructor, which we have not created. So alright, and here we are missing the destructor. That's a small oversight. Need to make one. Base besides destructor. Tilde here, tilde there. Okay, so we have our destructors which will be put here. We have the constructor, and technically the way this works is at first it will still assign the base vtable. That's the wrong one. This one. So we kind of enter the thing. So when we enter the constructor, it's like this thing. Then it assigns first the base. It does the base stuff, and then we reach the second one where it overrides this. And invokes and makes the rest, and then we are done. Okay, so we have our make subclass. So technically we could also first add here a make class. Then we need to change this slightly. That is, we need to give it the memory, because here we would know how much memory to give. Object. Okay, so we called it an S. Let's go with object. Then we don't have a return value. I just quickly copy this. Make mk subclass. And I could also maybe let's call it differently. Base. Yeah, and okay, that's more elegant. Right, and the usage of this, then we don't need this. This will be not used for later. Okay, we deleted a bit too much. Okay, so I just want to keep this part. Oops. Right, so assuming this worked well, so then we make base constructor from, and let's call it also here an object. Base constructor from object, and we call the next one the subconstructor. In principle, this could be cascaded, so that this one automatically calls that one. So maybe let's do that. That will be more in line how this normally works. Okay, now, so this one calls this one, and then it does its own thing. Okay, so we have created the object, and we need our initial value, so let's say it will be 1, 2, 3. Here we don't set default parameters, although for a better comparison we can here initialize also with 1, 2, 3, so that they will do the same thing. Okay, and now let's call a function, although here we are again missing the function 3 which we have defined here, so let's quickly create one. Base function 3. This is not a virtual function, so it doesn't have an entry in the vtable. Let's set the name. It was first it printed the two other ones, and then it printed itself. So now we need to call we want to use those two function calls because they are more elegant, but since they are not yet defined, let's define them quickly here. So func1 from this, and func2, oops, and func2 from this, and let's be also consistent. Let's just call this everywhere object. So before we use it too much, okay, cute. So we can now from our test here call function 3, pass it the object, and except for the lack of a destructor, we have some things wrong. Alright, this also wants the initial value, obviously. Oops. Okay, and as you see, we have both constructors being invoked and the function recalling the two functions from the right subclass. If we would here replace this with construct base, then it would call the parent functions from the base class as in normal C++ one would expect this. And now the one thing we are missing in this replica of an implementation are the destructors, which we started writing but didn't finish. So we have them here. Just thinking if we can better structure the whole thing, but no, I don't think so. So this thing will just write its own name, and this thing will do its own thing, and then it is supposed to call the base destructor so that it can also do its own thing. And one behavior we have observed earlier in an earlier lecture, I mean, is that when the destructor of the subclass is done with its own thing, before it calls the base destructor, before it does that, it will set the vtable back to the original value that it had before its constructor was ran, such that if the destructor of the base class would invoke any function, it will do this on its own functions and not on functions provided by the subclass. Okay, so let's add. So we have the destructor, so let's just use them. I'm going to do subdestructor in this case. Object, and then we can just free our object's memory so that we are great. Thing is, we did not define this here. We need to change the order of the things somewhat. I think we do it like this. I'll just here we remove everything. We just keep the definitions. The definitions are all that's needed for the tables to be made, because it can look those up later on. And then we put this here. Okay, that should already actually solve the issue. Yeah, and we have constructor, function 1, 2, and 3, destructor of the inner class, destructor of the outer class, and we are done. Okay, so obviously this is not yet mixing C and C++. We just kind of replicated the behavior. So the next step will be to demonstrate how this mechanism can work in combination with C++. So we will of course need somehow to create a C++ object and then somehow get its memory address. So it's not everything is kind of directly trivial, but it is simple enough. So we'll make a pointer global p my subclass. Can initialize null. Okay, then we'll just make this function create subclass my subclass. We can call something on it, but we don't need to. Then we will return the address. Obviously at this point it will kind of remain as a memory leak, but that is not a problem for the demonstration itself. So here slightly change the definition of this function. We add a second test. Test 2. And I just call test 2. And in test 2 we will want to get our object already created from this other function. And actually then let's just add our base 3 and see how that will behave. Now let's run it. And voila, it worked. More or less, well, almost correctly. So we see, of course, that func3 is our own implementation in C, because it was not a virtual function. So whenever we call it, we always call whatever is our own instance. But all the virtual functions, so of course those were still called from this function here, those two constructors, but those two functions here were called by our C code. So our C code successfully called a C++ function, two of them actually, and in principle if we would now have some values on our myvar1 and myvar2, then we could of course do something with them. So for example, we could just put a breakpoint here and see that those values are set to the expected values, and they are fully accessible. So any questions about this at this point? No questions? Okay, then let's continue. Let's make the demo a bit more formally correct. So let's call this make or new. Let's call this just new subclass. And in principle, we don't even need like a global variable to hold it. We can just really, and we of course want some int var, so that we pass this directly. That is more again, and then a void new del subclass, and it needs of course to take a void asterisk, or technically it should take a pointer on this, although a pointer on the base class would also be fine. So let's just call it delete my class, my class asterisk p, yeah, just p for pointer, and let's call it ptr. Right, and this will of course then clean up, so those two functions. And just for completeness also, let's just create a not subclass, my class. Okay, so my class, my subclass, delete my class. That's all we need. We of course need to this function we don't longer have, and this we can define before test 2, just without the bodies, just function definitions. And this of course here is invalid, but if we I think if we just put void here in its place, it should still end up working. Right, with the subclass 1, 2, 3 del object. Yeah, and now we have now it's correct. So we have the constructors and both destructors, and here of course our own implementation of func3 is needed. So you would if you would want to use the non-virtual function 3 of the other class, you would need a way to find out its address, which we could. Maybe we'll do that later, but for now let's focus on this. So if we change this to just class, not subclass, it will also work, just that then it will of course use the base functions and not use the other constructors. Okay, so let's make it more interesting. Let's call it test3, where we will start mixing things together. So test3. So we will need more test functions. We'll create an object ourselves. We will destroy the object ourselves, but we will want to pass it to the C++ side to do something with it. So we'll need a function void do something. Yeah, good enough name. Void asterisk ptr or do some object. Then we'll define our do something class here, but taking a base class pointer. And since it's defined here, it will, even though the type is not the same, here we have class, in the other one we had pointer. Just like with the destructor, it will work in both cases. So actually we should not have gotten rid of the demo function. Let's just keep it for let's just keep it here, just so that we have it. Don't need to use it, but it's just nice to have it. So we want to have to call this. But this will need, of course, to be. Actually, we can just use this directly. Zack. Yeah. Right, and here we said we will not return any value, just this thing. Okay. So now when we run it, did we do something? Wait. So we had our constructors. We forget to do something. Right, we forgot to call the constructor, obviously. Yeah, the destructor we called, we just forgot the constructor. Yeah. Wait, that's not, right, obviously that's not correct. We don't want the function definition there, we have it already here, so now let's call it. And as you see here, it's kind of now the inverse situation. We call our own constructors, we call our own virtual files, virtual functions I mean, but the non-virtual function is now the function that was implemented in the C++ class. And just for completeness we can like printf as my class var is equals %d, oops, %d \n, comma, pattern var1. Of course, if we would want to access var2, we would need to cast this, which we don't do now. So as you see, we can really, if we want, mix and match those things together, as long as we remember to do it correctly. So one issue, of course, is that as soon as we change here anything about those definitions, like if we would add another function in between, then we would need to change also our C implementation of this class. Another issue which we might encounter is that we will need to ensure that we are using the same constructor and destructor mechanism, so that we use the same memory allocator. So if we use malloc, then it usually would be fine, but if we would use some own heap or something, then of course then there will be a conflict, because the built-in mechanism like new and delete of C++ must end up using the same mechanism to allocate and deallocate memory that has been used by our own implementation. Okay, so let's see what else we can do. So we have already, of course, now manipulated a few things, but there is more what we can do. So for example, what we could do is we could make a class think that it is that it is a different type of class. So let's see how we do that. So we have here our C++ hacking. Let's get here this function. Let's copy it and make it a let's call it test 4. I think no, we had test 4. No, we didn't. Perfect. Test 4. No. Zack. So we define it. We call it. Okay, and for example, what we could do now is we could manipulate the class to think that it is, so we create a class of one type and then we manipulate it to think that it is in reality a class of a different type. So for that we will then, so let's first create, like, let's say this, so we know how we expect this to behave. But what we will want to do is we will mess with the function table to change, to really just swap it. So we know that this is like the first pointer that there would be. We of course need to find out somehow the address of this function table. So either we of course use our own function table which we have created, or what we could do temporarily is we create another instance just inside the scope temporarily. Void asterisk base table. Yeah. Okay. This should of course be pointed to a pointer. So we create our base class, my base. Zack. And in principle, we should get the vtable if we just get a reference on this thing and treat it as a void asterisk asterisk and one asterisk. There will be one less here. So this is a pointer on a pointer. If we want to get the value of the pointer, that should be correct. Let's, before we continue with the demo, let's quickly test if this gives us plausible results. Yeah, that looks correct. It should look correct. Let's see. So it's a pointer on the vtable for class 1, which has actually here a fourth entry for whatever reason. We can investigate it later, but that should be good. So now before we continue, let's just run this so that we remember the normal behavior. We expect the sub. So this we have generated here by quickly creating it temporarily. So we don't ignore those two lines, but the other two lines show us that we have correctly addressed the subclass. But now what we will try to do is we will try to overwrite it. So zack is equals base vtable void then my class, there is, wait, my class is correct. Why is this complaining? I think this is missing. And that was all. Because here we have somehow cut it instead of pasting. Okay, so let's run it. And as you see, bam, even though the thing was created as a subclass, now it is behaving as if it would be just the class itself, the base class itself, and not the subclass as it should. So this really demonstrates how this works. And of course, in theory, we could have saved the old value and then restore it and run the same function to get another result. So if you would for some reason want to just for one call make your class think that that it's of a different type or of the base type and not do something that it's supposed to do, then you could use such a very hacky approach. Generally, of course, none of those things that I am showing you today are really recommended because this is very error prone. So as said, if you change, for example, if you add one function, then I can actually demonstrate it. So let's go back to here, switch back to test. Which one? Let's say test 3. Sorry, test 2. Although test 3 is also fine, doesn't matter. Let's just take any of. Now let's go with test 2. So this thing obviously still works, but if we would now in test 2 add here to our class like some additional function which is somewhere in between, let's say function 0, and we'll call it of course function 0, and it's also not overwritten here, just one more. Then when we run it, we see that we have actually called now a function 0, even though we would have and then we called function 1 where we expected to call function 1 and 2. So if this would be like real code doing things, then we would have passed the wrong arguments and the whole thing would more or less end up in one big catastrophe and probably a crash. But since we are only printing, it kind of doesn't make a difference which function we call, so it doesn't crash. But as you see, if you would do such things, you would really need to keep your class definitions and your structures fully synchronized. Even adding variables might upset your class internally. So if you would want to access those variables from within your functions, so for example here if you would make those functions print something, and then they would of course then end up printing the wrong thing if the variable order has changed inside of your class. Okay, so this matched this, so let's quickly make it another demo, test 5, which will be even more elaborate. So we go here, we create our test 5 as a copy, test 5, but this time we will be just calling a C function which we define here, and hackfunc2. Okay. Need to pass the pointer to this thingy. Okay, so what we'll now try to do is we'll define a replacement function to function, something we want to be used instead of the original one. Hacked function 2, hacked function 2, and our goal will be to make this class call it. So let's get so one of course could naively think, okay, so we have here our object, so this thing should be basically of the type with a base type of the type base type. Object, so we have this thingy, we have our vtable, function 2 was at the index 2. Actually we can just use our index enum to access it correctly, and then we just overwrite this with a pointer to our function 2, and that's it. But that will crash, at least it should crash, yeah, because the way this works is these vtables, they are not generated for each instance, but there is like just one vtable for all the instances of base class, one vtable for all the instances of subclass, and the same with any other classes you might have in your project. So they are defined in a read-only part of your program's memory, and if you try to write to them, then you will cause a crash. And this is of course important, because if you would change such a vtable for any of your objects, this change will apply to all the objects in your entire program. So you would not, if we do this, we would not only break this one object, but we would break all the objects of this type until the program restarts. So obviously this would not be something that one should lightheartedly do. So the simplest way, of course, would be to create some new block of memory, new vtable equals malloc size of void asterisks times 4. That will be large enough for pointers. Then we copy the other vtable, so mancpl, comma from asterisk void asterisk asterisk ptr. We know that the first thing is the thing, so we also know that the size was 4. It's what not called ptr, we called it object. So object. Okay, so now we have our own new vtable on which we can with which we can do whatever we want. And then the only thing left to do is to replace the entire vtable of our object with a new vtable. Of course, the downside of this approach is that we kind of create a memory leak, because each time HEC2 gets called, it will create a new vtable. Let's quickly run it before I keep on explaining. And as you see here now, the function toCall has been replaced by a call to our function, to our HECT function too. But as I said, the thing is, if we would call this multiple times, then each time we would create a new vtable, and then each time we would of course waste some memory, because this thing will then stay there forever. If we know that we will be doing this only once, it's fine. Or what we also could do is we could define this new vtable as a just outside HECT vtable, and then here so if this does not exist, then create it and then assign it, or else it will always go here. Such a pattern is quite common and quite useful. You could also, in principle, just make a static function inside, static variable inside of your function, which then will also exist for as long as the application runs. But there is a catch to this, namely, as you might remember, we had threads in the last lecture and running things in parallel. And if you would call this function twice at the very same moment before the thing has been fully initialized, then they would both see 0, and then they would both do some initialization, and that might again leave you in a inconsistent state. So such patterns are only then safe if you know that you are not calling this particular function from multiple parts of your program. Yeah. Another approach what one could of course take is to manipulate the destructor pointer to basically just also hack it, and then make it delete the new vtable once the object itself gets destroyed. This is also a workable approach, but it's well, a bit more complicated. And of course, maybe the last thing that you might want to know how to do is, assuming you would actually want to change the vtable globally for every object, how would one do that? So let's we have here our normal myfunc. So let's define it and let's call it. Okay. And we have already a constructor function here. The question is which one we want to hack. We want to hack the subclass. So we had already used that here. Of course, we need a way to get access to this address. So void asterisk v table is equals asterisk. Actually, it's just as simple as this thingy. No, we don't. We need to dereference this. Void asterisk. Right. So we have now the address. Then the thing can get deleted. We don't care about it anymore. And now here, we would of course again have this, but again this would crash. So we need to find a way to not make it crash. And we can do that using a Windows API function. For this, we need to include. Let's include at the top Windows H. Windows H. Okay. With the virtual protect function, we can specify an address. This will be the tables of our table. We can specify now a size. So size will be size of void asterisk times 4, comma, and the new page memory protection. So page execute read write, the very unsafe version, and it saves the old value to the old variable, so that later, once we are done with our hack, we can revert it. Oops. Like this, and that's it. So now once we then call here this function to create a new instance and invoke it, it should still call our hacked function, and as you see, it did. So now no matter how many times we repeat this, it will always refer to our hacked function for the lifetime of the application. Okay, any questions? Okay, so if there are no questions, then let's continue. So this was mostly the whole C++ hacking part. So let's for default just remain at which test? Test 5. So that when we save it will be test 5. Zack. Okay. And we can then take a look on hacking some other things if this was interesting to you. So for that we will create a new project. Let's first let's keep that other open in case we want something from it. Create new project. Function hacking. Create. Okay. So since we will start a second thing, and usually we should take a break, which we never did. Let's say we make a short 5-minute break, and then we'll continue with the next hacking demo. Okay, I think that's enough of a break. So let's now see some other more exciting examples of hacking. So first we will include Windows H, because we will need that so that we can manipulate program memory. And first, of course, we'll just set up some very basic demo. For example, we can use the Windows show message box function to well, show a message box. Message box v. This is a test. Title MB OK. The thing doesn't do much, it just shows a message box with the text is the test and the title. So as you see, it's as boring as it gets. And now we will see how we can manipulate our program to call something else than the original message box function. Now obviously if we would just have our own program, we could simply replace the invocation of this function with whatever else we want to call. But for example, if we would have some library which invokes some Windows function and we want to hook into this operation to return a different value to the library, for example, or to make the library use some other value, for example, if you would have some sort of comport driver, which some sort of a library for a software that uses a comport, and the library itself is not open source, but it is limited in some way that makes it not suitable for a use case directly. For example, a lot of old code only understood comports 0 through 8. So if you would have like a modern system with 100 comports on USB adapters, then specifying comport 110 might be not possible with regard to how this library would want to operate. But what you could do is, for example, you could then hook a function which is responsible for opening a comport, and then ignore the comport which the library then supplies, and instead in some global variable have stored which particular port you actually want to open. You would substitute this, and the library would be none the wiser. It would think it opened COM1 while it has in reality opened COM101, for example. And to usually how those protocols work, it's completely opaque to the library through what it is communicating. So obviously one could say then just change the comport numbers in your operating system. That would also be a solution, but we are looking for a problem to our existing solution, so we won't do it the easy way, but we will try to make it the hard way. So first, of course, what we would want is we would want to create some own function which will be to be called instead of our real function. Here again we will use the extend C keyword, because all the Windows API is just a C API. So let me here on the safe side int inapi, but we will need to call it like my message box, for example. And for now we will just give it a body that doesn't do anything, just returns 0. And we will take a look how to get into that thing. So generally the way such functions are invoked here, we can maybe first put a breakpoint and step through it. The thing here, zack, is as you see, it's quite direct. We are jumping directly to where we want to be. Depending on how this is linked, there might be a jump table in between or not. In this case, there is none, so there is nothing like with this v table that we could just rewrite and then have this kind of instantly going where we want it to go. Oh no, wait, let's click the wrong button. Wait, is there or is there none? Call? Ah no, there is a jump table. So it's not made like with one function calling another, but it's made such that we have this thingy. It should be, yeah, this is a variable locally which contains, oops, which contains then the address to which we are jumping. But the thing is that getting the address of this thing, like we tried with the vtable, this will be, if it would be like a library, then it would have like its own entry for that. So our application would have like one underscore implement messagebox v, but the library loaded externally would have its own, which would not be exported. So this means that it would not be easily accessible from the outside. So the only easy way to, oh sorry, I'm getting a call, I need to pick it up. It was nothing important. Right. So the way generally we would want to manipulate this function call to make it work ultimately is we would try to override the code at the beginning of the function to direct it to our own function. So really, we will write into a system library image in memory to our own copy, to be exact, and manipulate it. So first of course we need to get this address. So there is a Windows function to get the base address of a loaded library. And as we have seen, the messagebox w function is located on the user32 DLL. So get module handle w and then L. Although we have to check whether this will work out of the box, because if the module is not yet loaded, but it is loaded, okay, then it would not necessarily work. So depending on how the invocation to the message box here is implemented, the module either is loaded from the get-go or would be loaded dynamically. In our case, it is already loaded, so we can proceed with retrieving the internal address. Void asterisk. Let's call it system, then the name of the thingy, message box w equals, and then we use another function, get ports address, which takes our module base, and it takes the name, which is message box v. And this thing will give us now a variable again with the address, similarly like the implement thingy here, just with one less indirection, which points us to the user 32 address, the same one as we have seen here in this internal variable that is used to make our program jump to this messagebox function. So at this point, as we could already start overwriting the memory, but of course we need to have a plan what we do. So first let's again go into our target function which we want to manipulate and copy the whole thing, because it's a very short function. So let's put it here in a comment. Zack. Okay, here we have it. Good. So as you remember from before, first things first, we will need to remove the protection. So what alt protect virtual protect address. We have size, where we could then protect the whole thing. Zack minus sucks, so it's 39 characters. Let's put it in a variable. Size t size t or size is equals 48. So this is how much we want to unprotect. Then new protection will be, as we remember from before, let's do it right, comma alt protect. And once we are done, before we use it, we can we can switch back to the old protection. But of course, before we do that, we need now to overwrite it with something. So we need to devise a strategy how we will be overwriting. So what I like to implement first is a helper object, which is quite useful. Union code lucha pb word pb word pd und 64 pq. Okay, and this thing is quite useful because it allows us to advance through some code which we are creating in real time. So just set one of the pointers. We are here in a C++ file, so we need to take care of the right castings. Okay, and of course we need to know what we want to write there. So when we think about the assembler code, one might want to use would be something like, for example, and then the address of our my message box, and then just jump to it. So really as simple as it gets. We save the address of our variable to a register, and then we jump to that register. Really easy peasy. But then of course to do it, we need to know the binary representation of these instructions. So for this, again, we will use here a online assembler, disassembler, to which we can directly feed whatever we want it to feed. So assemble 64-bit too long. Maybe it's just move. Yeah. Right. CDF. Yeah. So we see that this part 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8 is pretty much this thing. You remember how the computers are representing the numbers, that they change the order of the bytes when writing it to memory. So the whole thing is reversed, but it's 0, 1, 2, 3, 4, 5 until EF. And only the other two bytes which actually specify the move absolute tracks instruction. So we copy those two. And we use code punct. Now we can select which type we want to write. For example, word, these are 2 bytes. We can already plus the whole thing so that it will be then advanced once the write is done to the next entry, 0x. Here, of course, we need to remember to change the order for the writing, and we can make it all capital letters, except the X, just for it to look nicer. And now we want, of course, to write the pointer, so qword, again plus, so that the next write will go to the next thing. And then we just put the address. We need to cast it, of course, right type 64. And the last thing is jump rex, which should compile just fine as this. And this again are just 2 bytes that represent the operation. asterisk code punct. We write a word plus plus so that we advance the next thingy. 0x, and we change the order and capitalize it just for good looks. Okay, and of course it's in colon. So at this point we effectively broken the message box function, but whenever it's called it will bring us here, so we can put a breakpoint here and run the code. Right, we go for the breakpoint. We broke something. Okay. Okay, we broke something really badly. We will have to step through it step by step, but it should be correct with the address. Yeah, we will see. When stepping through it, we'll see what we have broken. So we go here, step, 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 step. We have here a move rugs with the address. The next instruction is invalid here. What? Q what? 64-bit? Q int? Oh, that's wrong word. That's very wrong. That should be just word and not double word. That was what we broke. Now should sorry. Sometimes my tongue gets caught up in itself. Now it should work just fine, but let's for safety just separate. And here, as we see, we have a move rugs, and then the jump rugs. So as it should be, the next portion of code is broken, since we were quite careless. But this already brings us here to our function, and we can also successfully return from it, and we get our return value. So at this point, we have already managed to overtake the function's execution. The only, although rather big downside, is that by doing so we effectively broke the function. So we will never ever in this program as is be able to show a message box ever again, which might be fine depending on what you are doing, or it might be a big problem. So what we need now would be some mechanism to repair it. Of course, one very simple, very straightforward approach would be to make some dummy variable uchar original message box fail. Paste fail. Original, and this should be GWait because it's global. Original message box fail. We said the size was 49. And then here we could then go with size of. And before we do anything, we just separe original. Where's our address? Here's our address, comma usize, and actually let's go with this as is, and this we just leave oops for here. And then, for example, from within the function, we could restore the original, so this works. But we have not defined this, so let's define this globally, because we need this address. I don't like the name. Backup. Yeah, this is, and no, my was also wrong because it's not mine; it's the original one. Right, much nicer. Zack. Now, of course, we need to kind of call it twice. This is a test. This is an other test. So first, we of course just for seeing the null behavior, comment out our hack. So we get This is a test, this is another test, and then we are done. And now if we uncomment our code, we will see we crashed. Sure, we crashed because we have protected it again. And of course, let's use this here as well. Not use size. Let's keep with size, but let's format it like this. Of course, we need to remember to protect and unprotect each time. We could have, in principle, of course, do it in a hacky way, like forget the last unprotect, and then just after we are done here, reprotect it. That would be an approach which would be serviceable. So here, of course, we arrive here, and then we just get this another test. So this already somewhat an improvement of our previous situation, because we can repair the function, and in principle we could even already use it. So we could just call the repaired function. If it would have the right type, let's give it the right type. Type def. What was that? Type def int. It takes an integer. It returns an integer int. vnapi asterisk p underscore message box w, and then we just paste this in there. Well, almost. Okay, then we can use this instead of void asterisk here. That will of course need a casting there, and here now we can call it as a function. Right, so we just pass all the old arguments, but except the test. Except the text. This is a hack, comma, bam. Let's make the title very screaming. Screaming needs exclamation marks. Okay, and let's run it. Now, bam, this is a hack. This is another test, and we are done. So, as you see, that is already quite flexible for the mentioned use case with the COM ports. That already might look like this is enough, but of course the reality is always more complicated. So there is a significant limitation with this approach. Well, first of all, we could of course call this thing, then re-hack the function, and then return. But that's not how you would do such things, because this would only work in a single threaded scenario, as we're using here for the demo. As soon as you would have a program that runs multiple threads which all might call this function, this hacking and unhacking it is a very bad idea, because one function gets called while the other function is just in process of either hacking or unhacking, and then you get an inconsistent state and the other call crashes. So this is not something you would want to do. What you would want to do is you would want to suspend the whole application except for one thread, do your hack, and then keep it in place forever, and then find some way how you can still make the original function work without like changing it all the time. And the method that is used here is called creating a trampoline. I mean, the backup we can leave, which basically will be a snippet of the original function. A snippet which we already have backupped it, but we might need to change it somewhat. That will do some of the initial operations of the original function, and then it will jump to the original function to an offset after the area which we have modified. So kind of we want to keep it functional. So let's do that. As we see here already, we have the whole function, and here when we count, we used 8 bytes here, 2 and 2 here, so 12 bytes in total. So let's see, we have here 4, 7, well, that won't quite fit, but with those 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, that's like 13 bytes. That's more than our 10, so we could in principle just save this somewhere, add a jump to the next instruction, this one, and use it. There are certain complications. Don't worry, we will run into them. But for now, let's just start with this very naive approach. So first thing, of course, that we will need is some memory, which we can execute and which we can modify. And there are approaches where you are trying to find like unused memory within existing images, but this is all kind of hacky, so we will just allocate our own memory and that's it. So we have here our address, we made a backup, we have the address of our function, so let's here allocate some memory. And such a function which is used to to execute the original function, this is usually called a trampoline. So we will call it here as well, trampoline message box v. We should initialize everything with nulls just for good measure. Okay. So, and depending on how we want to write our trampoline and other things of our code, it is customary to try to find some memory address which is as close as it gets to the original address of the original function. On a 64-bit platform, it is still advantageous to make shorter range jumps, mainly because most of the functions of the opcodes in the 64-bit version are still operating usually only with 32 bits, so you would need to always load the 64-bit address to a register and then jump to it instead of using simple operations, and it's just make things easier if we don't need to jump too far. So we'll make a loop which will try to allocate an address as close to our goal as we want. So char asterisk address is equals char asterisk. Here we will take the system address of the message box, so we want to be close. We don't give it a condition here, and 0x1, and we will go in increments of one page to find some address where we can allocate it. Oops. Actually, that looked better like this. Yeah. So our trampoline is equals. We need to cast it. We have the right thing. Yeah. Here. To use the virtual alloc function without a space, virtual alloc, which takes the address where we want to. Allocate the memory, some size. Our trampoline will not need too much size, but I mean, for simplicity, we could really just always go with the same size here. Effectively, of course, virtual alloc will allocate at least at the granularity of a page size, and the way a virtual alloc normally works, it will actually allocate at the granularity of a 64 kilobyte with regard to the address space. So it is a bit wasteful, but for our purposes it doesn't make really a big difference. And then of course we can specify some flags which type of allocation we want. So we want mem commit and mem reserve, and then the protection, as we already remember, page execute. Oops, that was not quite right. Other read. Let's type it out manually, and then we test if it was successful. So, oops, if this memory could be allocated, meaning that it has not yet been allocated before, and of course that we have enough memory in the system, but we always assume this is the case. So if this is not null, then we just break, and we are happy. Okay, so now we have some memory to work with. Use the same trick as here with our code. We can reuse this code object as many times as we want to just assign a new pointer. The whole thing only takes as much memory as one single pointer, so it's extremely useful and very efficient. It's a very elegant solution in my opinion. Okay, so let's see. Let's keep the thing there up on top inside. So So asterisk code punct. That's 4 characters, so let's the double word plus plus equals 0x 38 EC 3 sorry 8348. So we just typed the first opcode in the reverse order. We can actually write down what it does as a comment, of course. Maybe tap this a bit. Yeah, something like this. Yeah, good enough. Right. Now the next operation is a XOR operation. So, but it only takes 3 characters, so that's kind of meh. The annoying thing is that we don't have a type with only 3 characters. So first we write a word 0x with the first 2 things 3 3 4 5, and then we write a byte of the missing 0x db. Of course we could also just write 3 bytes in a row, but we kind of try to make that whole thing as short as possible. Okay. The next one is a longer comparison operator. It has 7 characters, so we can write a double word. Or I will do it in a particular way, and then later explain why I did it like this once we run into the issue, which we will do inevitably very soon. Code punct word plus plus is equals 0x 3944, then byte 0x 1d, then a word, a double word 0x 0007 56 DA should be correct. Suck. And we of course again comment what we did. But until now we only did what the original function also did, so we also now need somehow to jump to where we want to jump, and as we have counted here, these are 13 characters. So we will define as a oint64 underscore trampoline target is equals this plus 13 plus 13. Oops. So this will be the target where we want to jump to, and now we of course want to jump there, so we can copy kind of this code here already. Since we are not doing anything really different, we just load to a register and jump there. Maybe 2 underscores for good measure. It looks better. Yeah, and of course one thing to keep in mind here is that if you would have seen this code here use the rex register for something already, then of course we cannot overwrite it here and jump to it, because then it's needed. Then we would need to pick another register for our invocation of the rest of the original function, which does not cause issues. Or what we also could do is we could use some sort of jump table or something to jump to. So let's quickly play around with the assembler a little bit. So let's say we want to jump JMP to 0x, and if you try to build to compile this, as we see, it doesn't like this. So here, for example, I said we can jump to an address within a 32 within a 32 bit long address range, but jumping to something that's further away just does not compile. Although this thing here is not compiling correctly either, because we should have the value. So let's see, there was a second, this one. This one is more reliable. Zack. Right, so this again will not be happy, but this is happy, and it more or less takes our value. The value is slightly modified because it takes into account their own length of their own instruction, and it is a jump to an absolute address. So it is jumping. Sorry, it is a jump to a jump relatively from where we are right now. So it's not jumping to an hard defined absolute address, which also is kind of a problem. Might be a problem if you want to create such functions. One thing one could, for example, do is to jump to, how was it the syntax for that? Plus, let's say 16. Yeah. So what we can do is the instruction pointer register always points to where we are right now. This thing compiles to 1, 2, 3, 4, 5, 6 characters. So let's make it plus 6. Doing the plus 6, it actually might work with plus 0. So the idea is that as the next entry, so as the next entry would just really keep a literal in there, and it would basically just jump to return pointer. It uses, I think plus 0 is correct. I think plus 6 would not be, because the way this works is, I think it evaluates the address after it incremented the RIP register already by its own instruction length. So this would be, we can actually try this approach if we want to, because it doesn't waste a register. So we just need FF 25 and then 4 zeros. So instead of this approach, we can use the other one, 25 FF, and then word, double word, code, asterisk code, pair, double word, plus slash 0, and then we need our address, which is still the same. Okay, so this is then, we said we write it here, jm pair to pair plus 0. Oops. And let's just quickly check if we are not consistent. This thing is too long, so let's, no, I think this was correct. Right, so this should also work well, but we'll step by step through the whole thing. There is one thing which will cause a crash in the way we did it here. One I will explain once we run into it. So we have here this thing. We call this trampoline instead of the original function. Put a breakpoint here. We forgot one thing. Ucha this is not Ucha this should be Win64. It was a small copy and paste bug. Right, okay, so we arrive here at our hacked function, and now we want to go to our trampoline. So we call this thing, and we have here the XOR, the move. Wait, no. That doesn't look correct. We get here a sub and XOR and not XOR and move. Did we do this correctly here? Double word with this, word with this. P is initialized to the trampoline. Jump target, that should be correct. Let's try it again. Okay, so we're gonna step, 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 step. Okay, team. I think I just didn't type this up correctly. The first thing is broken. So we need to reverse the order. Wait, so 3, 8, it looks right. EC, 3, 8, EC. We are missing one character somewhere. 4, 8. 4, 8, 3, 8. Yeah, now it will be correct. That's not the error I mentioned earlier. There is a systematic error in our code. Okay, so we have our subtract, we have our XOR, that's fine. We have our compare, and we have our jump to, yeah, and jump plus 0 is correct because the address we jump to is the address here. And here it just shows garbage because it's basically just the address and not a valid instruction. But as soon as we try to executing this jump thing, this compare thingy, as you see here, we also crashed. Why did we crash? Well, the answer is quite simple. Let's see what we are doing here. We are comparing the content of the R11 register as a double word. Since R11 was XORed with itself, we know it is 0. This is like a hacky but very commonly used way by compilers to assign 0 to a register on x86, that is. Of course, with other platforms this works differently, but with x86 this is a easy method, and most important, it only uses 4-bit 3 byte, I mean, and not more. So a normal assign operation would like use usually a few more, plus if this would be actually done with one of the registers that are available in the 32-bit architecture, that would be even without the prefix here, so it only would be 2 byte. So it would be really extremely efficient, and that's why they do it. So we know this is 0, and then what we're doing here is we are comparing 0 to these variables. So basically to this variable, but the way this addressing is done is relative. So if we throw this code here to our decompiler, to a better one than Microsoft's one, we see that this is really what's written there, like with all the details, so to say. The other things will decompile pretty much the same thing. Like for example, if we fed this thing in, it will just give us the same thing we already got. But here it really tells us that we take a value which is relative to the instruction pointer. It's in principle the same trick we used here, just that the value is somewhere within the 32-bit range of the instruction pointer. But if we move this to an own memory block, as we did here, then of course the RIP, the instruction pointer, will not have this exact value, but it will have some other value wherever we are, meaning that the jump there will not be possible to execute the jump in the way you might want to. So what we need to do is we need to find out the displacement of our own code block in relation to the original code block, and then modify this instruction accordingly. So Win64 trampoline displacement is equals uchar, not uchar, Win64 is just fine. Tram message box v minus Win64 this message box v. So this gives us our own displacement, and in principle that already might be enough. We just of course need then to apply the value to our original value. So we have here this value, and then we just subtract from it our displacement. And then it should be corrected. So let's see if this helped. Zack. Zack, 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 zack. So we jump here. And now let's see. The compare function worked. We didn't crash. Then we jump to JE. Probably it's the right thing. Let's compare. Yeah, the next one is JE. It here kind of failed to interpret this opcode because the code is a bit broken in the area between what we overwrote. I think we overwrote like 10 characters, so until here. And those 4 we left untouched, so it's kind of garbled. And depending on from where you come, it might be able to properly interpret them or not. In this case it cannot, so it's showing here this question mark. But if we run it, bam, this is hacked. And when we press OK, then we will again get here. So now without breakpoints, we just get the same message box twice. We could of course make it a bit more sophisticated, so we could add a counter wherever, and let's say if this plus plus is equals 0, so it was the first time, then this is hacked, and don't do it any second time. So this is hacked. Wait, we forgot to call the unmodified version in the else case. So in the case where we don't want to modify the execution, we just don't do anything. So this is hacked. This is another test, and we're happy. But I'll change this. So if this is 1, because like if it's the only very first one we want to hack and it's single threaded, we already seen how we could do it. So here, now the first invocation, even though it goes through our detour function, it behaves normally, and the second one says it's hacked. And if we would have a third one, then it would show again that it's fine. And the general idea would be, of course, here that instead of, for example, counting how often we have entered, what we could do instead is that we would try to for example, evaluate the arguments that have been passed, and then based on these arguments make a decision what we want to do. So let's implement here such a nice hacky test case. Let's ignore that. Oops. So if message box fail now question mark title ember yes no, and if this is id yes, then tone -1, or maybe even for another message box failed ember okay icon that was, I think, MB icon. Yeah, genau, MB icon hand. Or the other case, we don't failed. Success, but then we want another icon. MB icon information. Yeah, okay. And for now, we will comment out this approach, so that it just doesn't do anything. So we get, you want to fail? No. Success. And the icon hand didn't work. It should have shown us like a stop sign. The icon information worked fine. Okay, icon hand, why would this not work? It should work. And we could go with an exclamation mark. If the hand doesn't work, let's go with the exclamation mark. No, it of course, sorry. It's the wrong function, it's this one which doesn't work. So let's here just add an icon. mb icon question mark. Yeah, that's nice. Yeah, and now we say yes, and then we get our failed. Perfect. Okay, so for example, one way we could do is we just know the string that the thing will ask. So we test here if what's the s sample string 1 is lp text. Want to fail now, and if this is 0, so if this is so if the check matches, then return id no. The idea here is now that we kind of suppress the question message box and return the right value for the whole thing to just continue and say that it was successful. And suck. And voila, it's you have effectively bypassed a message box. And of course we could make such modifications with anything we want. So it doesn't need to be only limited to a message box. We can override any function of which we can get an address. In the practical use case, of course, one would not want to write so much code by hand. So this is, of course, not the most efficient way, because you would want your code probably to work on various versions of Windows. And for example, the value here, basically with every Windows build this might change. By how much is also not predictable. So one could of course say that you would copy the original code, you would know which opcodes come, and then here extract the value. So in principle what we did here is really we just copied the beginning. So what we could do is instead is we could copy the beginning and modify it. But for this again we are making an assumption. If they change something, that will change the order of opcodes or change the opcodes or something, then again we'd end up with something that will just crash. So the typical approach here is to use some sort of library which approaches this problem in a much more sophisticated way, basically by disassembling the begin of the function. So it should understand every single opcode it might encounter and know how to modify it if it is relocated somewhere else. There is such a library, for example, offered by Microsoft called Detours, which does this. It's on GitHub. Detours. Okay. It's quite big, but it works also for every architecture that is relevant for Windows. So x86, 32 and 64-bit, ARM 32 and 64-bit, and even the old Intel Itanium architecture, which is no longer really in use. So I don't think Intel is still producing those CPUs, and then modern versions of Windows are not longer targeted for this platform. I think Windows XP and maybe Vista were. I'm not sure if even they made Windows 7 for Itanium, or if they already considered this to be a dead end. And as we see here, they also added support for ARM64 EC. This is a special case, which I think would be out of the scope here to discuss, but actually I'm glad they did, because that might be useful for some of my open source projects. So I'll remember to update the library. But as I said, this is a rather big library and quite complicated. There is another one which one also can use, is called Minhooks. But if I recall correctly, this one first of all only works for x86 and x64, so the Intel/AMD instruction set with 32 or 64-bit. It does not work for ARM or any other architecture, and if I recall correctly, the way this is made is it is a hooking library made specifically for Windows APIs. So the way it is done is they have just analyzed all the Windows APIs and the prologues of the functions, and have found out and made like a cookbook. So if it starts like this, patch it like that. If it starts like that, patch it like that. And since the variety of the potential function products in the Windows API was rather small. This manual approach worked, and this allowed them to make a very compact library which does not actually need to disassemble anything. It just looks, if it knows how the function starts, and if it knows how the function starts, it knows what to do with it. And if you try to patch a function which it doesn't know, then it will just return you an error that it doesn't know how to do it, which is obviously already a great improvement over our fully manual method, which will break with any change to the system. So basically, install a Windows update, and this will probably be already broken. But as said, it's much more lightweight than this DTOS library. This one really works with dissecting the header, and it could in principle patch anything you throw at it. Maybe with some exceptions of something extremely esoteric, but if you have a normal function that's generated by a typical compiler, that should in most cases be perfectly fine. Now, of course, given that ARM is becoming more and more popular, especially with the modern Snapdragon-based Windows laptops, then I would of course recommend you to use this DTOS library, since if you then compile for another platform, it will work. That said, of course, since this Windows platform can emulate the Intel instruction set, if your application and your libraries are all just x86, then this will also to some extent work. And if I recall correctly, the Windows libraries on these ARM platforms, the wrappers for the functions are made such that you can hook them, and they have a very predictable prolog. So given that this was updated 2 months ago, it should probably work in such an emulated environment still. It won't work with native ARM apps, obviously, but if you're just patching Windows functions inside a x86 application, then this would work just fine. Okay, so this much to this. I think we don't have time to start the next thing I would like to show you with regard to hacking thingies. That would be how to manipulate an application for which you don't have source code. So this approach here really is more limited to manipulating things inside your own application when you load some library, which you might not control, but it does not really allow you to manipulate a whole third-party application. So coming back to our initial example, some control software for some old hardware which only allows you to select COM 1 through 8. You might want to be able to patch it such that it will always connect to, let's say, COM 108, no matter what you enter in the UI. So this we will take a look in the next lecture, how to inject code into another process. And just to be clear, this is just like a demo. So your homework is the final project which you got, and you should focus on that. That's why my English is broken today a bit. Therefore, what I'm showing you in the lectures now after the project was assigned are things which you might find interesting, but there is no homework that will come out of this. So you don't need to be worried that you will need to do those difficult things on your own. It's just to give you some in-depth and practical look on things that you are on the verge of being able to do with what you learned in this lecture. But you don't need to exercise those skills just yet. But if you at some point in the future find that you might need to do one of such things, then you know where to look. Yeah, and I think since we had only a very short break and there is not enough time to start another project, we'll finish today a few minutes early. Unless you have any questions, so you can of course ask questions now if you want to know something. We have time. Yeah. No questions? Okay, no one asking questions. Then I would say we will finish. I will upload the recording and the 2 projects to Moodle, and next week will be the last lecture, where I said we will try to manipulate some already running processes. And that's it. So have a nice evening, and we'll see each other next week. Bye bye.